Okay guys, sorry for the delay. So this week is the 9th lecture of our term. Again, in crazy circumstances, I apologize, it's like 5:15 in the morning. It's really hard to get a long enough time access in front of the TV without kids around, and I've tried all kinds of scenarios, and early in the morning turns out being the absolute best time. There is a chance one of them will totally screw me over and wake up and come down while we're still filming this. We'll deal with that if we have to. So today's lecture is talking about concrete, so the construction material concrete. And when we're talking about concrete for us, we're usually talking about reinforced concrete. So not toppings, not sidewalks, the actual structural concrete material that has reinforcement placed inside it. Last week, we talked about composite materials, and that's when we go through lengths where we have that shear plane transfer between two elements that allows us to transfer loads in a way that makes them behave as one element. Otherwise, they may just share load instead of acting compositely, which they still share load in a sharing load phenomenon, but by acting compositely, especially when it comes to bending and stiffness for a bending element, we see a drastic improvement in performance. So concrete is a material that we make composite in actually two parts. The concrete material mix is actually a composite material. We've got sand, we've got limestone, we've got gravel, we've got water, all having a chemical reaction to become a composite material. But that almost batter, if you want to think about it, that has those rocks in it, or that gravel, forces those gravel elements to act compositely. And then, when we did all of those testings way back when, we saw it was great for things trying to squash. It behaved really well. It could carry a lot of load for what was a relatively easy material to make. Obviously, steel is way stronger, but it takes a lot of work to make it. Concrete's relatively easy to make. The big problem with concrete was it had zero capacity and tension, or pretty darn close to zero capacity and tension. So if we have a bending element, that bottom side that's in tension, all of a sudden causes this thing to fail. So great for compressive elements, so columns and pillars, which we would often see kind of in ancient construction methods, but try to put it in bending in any way, and it just didn't work at all. They came up with some good tricks using concrete as mortar between blocks and having keystones, but we know, based on the fact that that was kind of prized information, that it wasn't obvious without kind of the data that we have now. So we said, what behaves really well in tension? Somebody said, oh great, how about steel? So we started putting bars of steel, which behaves really well in tension, in the bottom of the concrete. And so now, the concrete at the top can take the compression, and the steel at the bottom, acting compositely with the concrete, can take the tension. And now we should start to see a really well-performing structural member, and that's what we're going to talk about today. So before we do that, I'm just going to kind of give you a quick breakdown of what the hell concrete material is. And we're going to talk about the concrete and the reinforcing separately and together. And then we're going to start talking about compression design, and then we'll talk about bending and shear design. And then I just want to show you some of the inherent advantages, depending on how you think about it, but often advantage in building with concrete. We talked a lot about kind of just the way we detail steel naturally gives us a lot of the things we like to design with. Up until now, almost everything we've talked about has been a pin roller connection. We're going to see that that is different when we talk about concrete. So, reinforced concrete. For compression, as much as the concrete is great for carrying compressive loads, we also, since it's there, use the steel. Well, why is the steel there if the concrete's so great? I'll talk about that in a few minutes. Tension, only the steel. We use the steel for the tension completely. Shear, we can use the concrete by itself, but since we often have steel in there anyway for crack control, and I'll talk about that, we will use the steel to kind of help out our calculations, since we've got things in there anyway to limit cracking. And once we're doing that, we might as well use the concrete and steel together. If that still doesn't work, we need to add more elements, more steel elements. One of the really interesting ways that concrete can fail, different from most of the materials we talk about, is actually in shear. And I showed you guys images at the beginning of this term and last term, something called punching shear, which is when our big slabs actually slip down past our concrete and our concrete columns. And that's often why we see drop panels and capitals at the top of our concrete columns in places like parking garages. There are non-structural elements in the reinforced concrete. We will put shrinkage reinforcement in. So concrete, being a material that we're making kind of on the fly, it does, as it cures, shrink. You can imagine that chemical reaction using up the materials, and there's off-gassing that goes with it. Not a lot, but there are materials that kind of come off of it. Heat is one of the things that actually comes off concrete as well when it's curing. And when it does that, as it cures, engineers get really mad if you say dry, while it cures, it has a tendency to shrink, which has a tendency to make it crack. We all know owners hate cracked concrete. In fact, in your career, if you start being a practicing architect, your first lawsuit against you will probably be because concrete cracked. Not because it's a good lawsuit, but it will probably be one of your first lawsuits. It's one of the top things engineers and architects get sued for: cracked concrete and cracked drywall. Not actual structural failures, but things like that, and envelope and wet and gooey things. But those tend to be some of the most common reasons we all get sued. So be smart about your reinforced concrete, and always, always, always tell the owner concrete cracks. Never ever promise anyone uncracked concrete. We can, with really extreme measures, get something that is almost looks like it's not cracked at all, but that is an extreme method of construction, and we don't do it often. And even then, there will still be some cracking. It's just a little bit harder to see. So straight up off the bat, concrete cracks 100% of the time. But we can try to control that crack. So if over a 1 meter distance, we're going to get a 1 centimeter crack, which sounds huge, but we don't want that. What we can do is put things in place that means we'll have 10 1 millimeter cracks instead. So it's spread out over that 1 meter distance. So we can do things to try to control the cracking. We're not stopping the cracking or changing the amount it cracks, but we will put the cracks, or attempt to put the cracks, closer to where we want them. Anyone who's seen a concrete floor and seen saw cuts knows we're doing that to try to control the cracking. Concrete sidewalks, those aren't poured. They do several strips as one piece of poured concrete with a joint in between it. But those other joints you see are just cut in or pressed in to try to control where the concrete cracks. But we all know it can crack in more places than that. The other thing that we need to know about structural concrete is that we need cover. Cover is fire protection cover. So we know that steel is susceptible to heat. If it's in too hot of a situation, it loses its capacity or its strength at a drastic rate. So we try to protect that steel using the concrete itself. Concrete is actually great in fire, but because the steel is doing the tension work and in bending, that's half of the job we need done there. We need to lift that steel up and bring it in from the sides to try to protect it from the fire that might occur around it. So great, why wouldn't we just bring the steel up as far as we possibly need to? Well, having that steel down is where our D is. Remember, our depth D is always what really helps us for things in bending and in stiffness. Remember, S is BD squared divided by 6 for a rectangular bending element. And for stiffness I, it's BD cubed divided by 12. So that D is a really, really important dimension in our geometry of our object. We want that steel somewhere as close to the bottom as we can get it, but lifting it up enough to protect it from fire. So I'm just going to go through this quickly. People always ask about it, but it's not really what I want to spend a lot of time on, but you can look into this more if you want. So Concrete properties. It's made up of aggregates, so coarse and fine aggregates. We have water, or you'll often hear it referred to as the water content or water-concrete ratio. So that's usually talked about as a percentage of the makeup that is water. Sand, which is different than our aggregate. Portland cement. We add entrained air, so little tiny bubbles that helps us out. And then we can add admixtures. So these are things that have been coming out slowly over the years, and they've gotten better and better. We can make it cure faster. It comes with side effects of that. It can crack faster or bigger or in less controlled methods. We can add plasticizers, which makes it flowable. If we have something with all kinds of steel in it, we need to get that concrete down in it. We don't want to end up with big voids of concrete, which is a big problem in concrete casting. We can add a plasticizer. One of the other things we do to help limit those voids in concrete is we vibrate it. So literally they take a big ass vibrator and stick it down in the concrete, and it's somebody's job to just go around vibrating the concrete to make sure it all gets down to the bottom. We have to be careful when we vibrate though, because we don't want to separate out our aggregates. So we don't want to over vibrate something either and have our aggregates separate where we have big ones clumped and small ones clumped. If you've ever taken a bucket of sand and that has gravel and sand in it and kind of shaking it around, you know it'll start to kind of tear or get layers in it, and you don't want that to happen. We can add fibers. Fibers are really helpful for crack control as well. They do the same thing as our steel. The problem is when we finish our concrete, or we polish it, or kind of finish it up, we end up sometimes with little fibers sticking out. And so if you've ever been to a Home Depot, you might have seen the floors where they actually have steel fibers in it. And you can see in some spaces that there's actually a little piece of, it looks like a little kind of cut of wiggly steel in the top of the concrete. Well, if that sticks up just a little bit, you can imagine somebody walking on it being a disturbance for the foot, so they have to make sure none of those stick up. So here's the typical proportions of all of those materials within concrete. This is still that horrible cold that's been kicking around since long before the pandemic, and it's still bothering me a little bit, but seems to be clearing up a little bit. So here's an example of a concrete mix. Now, the structural engineer gives guidelines about what needs to be happening in that mix. So we will give the strength required. We will say that there's a maximum aggregate size. So that's the biggest piece of rock that can be in it. We will say the water to content material mix. We will say what exposure class it is. So if it's going to be outside, we might do different things to it, or different admixtures to it. If it is going to be near corrosion elements, salt. Salt is a corrosion element for our steel. We'll tell them to put a corrosion inhibitor in it, and that would often be represented in our exposure class. And then we have our air entrainment percentage that we'll put in there. That's those little bubbles. And then one of the ways we kind of help test to make sure our concrete isn't too gooey, but also gooey enough, is a slump test, where they actually take a bucket full of the concrete, and right there while it's wet, they turn it upside down and take the cover off, and we look to see how much it slumps. Or if you've ever taken a bucket of sand and turned it upside down, if it's not wet at all, it slumps almost 100%, or the full depth of the bucket. You might get a pile of it at the bottom. If it's too wet, it will slump too much as well. If you're at the beach on that perfect, gorgeous day and your sand is just wet enough, and you fill up that plastic sand bucket and you tamp it down, which you've probably done, and you turn it upside down and lift it up, you'll get no slump at all. Now, we don't want no slump, because then it can't get down into all of those little bits. So we definitely want some slump. And so this is how we, kind of as a quick check to make sure that the general consistency of the concrete is okay. Remember, every batch is kind of made on the fly. It's kind of mixing itself up on the way from the plant to the site. And where we're adding things like water and air to it, a humid day can make a very different concrete mix than a dry day. So these are kind of the loose recipe mix for it. I don't know if anyone in the class makes bread or pizza dough, but I know that I can make 2 batches of pizza dough, one right after each other, and get a completely different crust for my pizza. Concrete is like that. But we know generally one type of recipe is better for pizza crust than for a sourdough bread, but there's always variety slightly within that. Think of your concrete mix as something like that. So what do our stress strain profiles look like? So concrete, we can see here that we've got our reduction factor for concrete is 0.65. 0.65, because like I said, it's like our pizza dough recipe. It's gonna be a little bit different every time. And what happens if it's on the crappy side that particular day? So we use a reduction factor of 0.65 for our concrete. Here is the stress strain graph for it. You can see that it kind of comes up. We get a brittle failure, obviously. One thing I'd like to point out is that this is only for compression. Concrete essentially has 0 for its tension side of the stress strain graph. Most of the other materials we've seen are pretty darn close, whether they're in compression or tension. We call this F'C. So F'C is, instead of our Fy that we talked about for steel, or when we were talking about wood, we had Fc or Fb or Fv, talking about our ultimate stress that our piece of wood could see. For concrete, we use F'C. Every industry kind of did a little bit different. Concrete is talking about F'C. And here you can see they graphed the reduction factor applied to it, just to show you a sense of how much kind of buffer we give ourselves in the design of our concrete itself. Reinforcing bars. We have here pretty much our stress strain curve for steel. They kind of cleaned it up a little bit. We know what the stress strain curve for steel looks like. These are not to the same scale, obviously. Concrete tends to be around 30 MPa, and our steel, we know, can often be up much higher. Our ultimate, Fy for rebar is actually 410, and we're going to talk about that in just a minute. Pre-stressing tendons, we're not going to really get into that at all, but we can cast tendons into concrete and stretch them and make them pull the concrete together. So we can take the concrete that would be in tension and force it into compression by trying to push it into itself by using these tendons. Remember I said there is a way that we can get concrete that almost seems like it's not cracked at all. We can do post-tension concrete where we would put stressed tendons embedded in the concrete with big plates. We also use pre-stressing tendons cast directly into the concrete itself for our hollow core slabs, for example. Here is the actual full stress strain curve for concrete. I just wanted to show you this kind of for reference. Here's our tension side. We essentially treat this as 0. We say we have 0 strength in our tension side of our concrete. Here's our compression side. Here's our peak compressive stress. They've drawn it here the way we've always drawn stress, but we know that for concrete we use F'C. Concrete is a brittle material. It doesn't have a plastic zone. It will fail at its ultimate stress. So what are these concrete properties? So F'C is usually between 20 and 40 MPa. A lot of the times we work with 30 to 35 MPa. And we'd specify that. The engineer would specify that. And we have pretty good guidelines on what we need where for different types of concrete. E, or our modulus of elasticity for concrete has a wide range. It can vary from 14,000 MPa to 41,000 MPa. Again, that's a huge range. We know our steel was 200,000 MPa, so our concrete is not as stiff at all. Oddly enough, because we need a lot of concrete, because it's not very strong, we actually end up with a pretty stiff system in the end. Modulus of elasticity, I can't tell you what it is perfectly, because it is dependent on the strength of the concrete. There's a relationship there between those two things in concrete. And we have an equation for working it out. I am not going to bother you with that. I will always tell you what the E of the concrete is that we need to work with, or what E we might need to work with. And like I said, the reduction factor for concrete is 0.65. Again, the tensile strength is 2 to 5 MPa. We assume 0. And flexural strength, there is a little bit of flexural strength for concrete itself, but we don't really use it. So let's look at these different F' seats. Footings and caissons, we expect 20 MPa. They don't really see much bending. They're embedded in the earth. They don't have access to a lot of the kind of wear and tear. They're usually all about a load in compression, which we know is concrete's best kind of way to behave. So we'll use the lowest kind of concrete mix that's readily available. Foundation walls and slab on grade will often spec a min of 25 MPa. Frame slabs and columns, we'd use 30 MPa. And then as we start to get into those big concrete buildings that we see, especially going up in Toronto now, we're talking like the big ones, so mid-rise, high-rise, we'd start speccing much higher concrete strengths. Again, it's almost a different science in of itself, but mostly it's all about having that strong concrete. We have to add different things to it. We use different rebar, so it's not the most common way to build with. Rebar. Fy of rebar is 400 MPa or 410 MPa, but we'll use our 400. E, 200,000 MPa. Our steel, always 200,000 MPa. Our reduction factor is 0.85. Now, I know for almost everything else we did in steel, our reduction factor was 0.9. Rebar is kind of squished a little bit. You can see kind of a line on it. We've got our ribbing on it. So it's not quite as perfect as our other steel is. We don't have all the same kind of high level of tolerances that we do with the rest of our structural steel. So we use a slightly lower reduction factor, or we reduce its capacity a little bit more. The sizes that are available. In Canada, we refer to M, which is pretty much their dimension or their diameter in millimeters. It's close, it's not perfect. So 10 all the way up to 55 M bar. If you're in the States or Europe, they have different nomenclature or different classification systems, but they tend to be very similar. 10 M bars are really floppy. If you put them in a slab and you tried to walk around, the bars would bend. We don't like using 10 M bars if we don't have to. We tend to only use them for shear reinforcing, so things that would be on the inside face or for stirrups, not the things that are the main job in the system. Our spacing for our bars, remember we need to get our aggregate in and around these pieces of steel, so we need to make sure that, that we have space in between them. So we spec like 2.5, I'm paranoid that this isn't recording and I'm wasting my time. We're good. I just would have sucked to have finished this and realized that I hadn't pressed record. Like I said, it was 5:15 when I started this. So we can get as close as 2.5 times the diameter of the bar close together. So we need that gap in there. Don't forget, that's center to center, so there's still the dimension of the bar, and then we need that gap in there. There's kind of really good rules around how we space these things, and sometimes we know how much steel we need, but we still say, oh, we're going to throw a bit more in for some other reasons, as long as we meet these criteria. The general philosophy on how to use our reinforcing is fewer large bars is cheapest, but more smaller bars works better. Remember, we can kind of spread out how we crack. We make sure that we've got our kind of use of material distributed throughout our system instead of localized. So large bars are cheaper up to a point. 45 and 55, even 35s are expensive. So I'm talking about the 15 to 30 M bar range. So more 30s would be cheaper than a bunch of 15Ms, but a bunch of 15Ms are easier to work with. So how do you know what to do? I don't fucking know. It depends on the day, what's going on, what the specific use of it. Is it a slab? Is it a beam? Is it a footing? What's the access to the site? So not always an easy choice, but you start to see that there are kind of pretty general ways these things look, and you probably just follow whatever the precedent is for a lot of those things. Again, I'm not going to make you pick those things, or if I do, it would be a pretty obvious kind of selection method that I'd want to see come out of that for you. Like I said, the 45s and 55s, they're available, but they're a last resort. When we have concrete in tension, if we have a bar that's this long, they come in kind of set lengths. So if we have one that's this long and we need to put in another bar, we can't just butt them up against each other because there's no steel right there. We have to lap our pieces of steel. And the bigger the bar, the longer we have to lap them so that the tension that's in that bar can transfer out into the concrete, and then the concrete can transfer it into that bar. So we have to have a lap length of steel in compression or tension. And to lap a 45 or a 55 M bar is huge. So what we really want to do is have them butt up against each other, but we'd have a failure there. So we actually have to buy special couplers that force them to act together as one long piece of rebar. So, what's happening with a concrete column in compression? The concrete and steel share the load based on stiffness. Remember, we talked about that last week. We did some calculations around concrete columns in compression. We're going to get more specific this week, and I'll show you that it's not quite as easy as what we were talking about last week. There's that whole buckling thing we need to talk about. And that stiffness is based on the relative area of each material and the material's stiffness. And so sometimes we'll convert one into the other to make our calculations a little bit easier. Steel has two jobs in our concrete column. The longitudinal steel carries the load, so that's the uppy-downy steel, is going to share load with the concrete. We put ties in, so things that kind of band our steel together, whether it's a square profile or a round profile. So our ties if that's our concrete column, paste that one, our ties will go around it like that. And in a rectangular column, we'd probably do something like that. Again, look, these are closed ties. We need to do something to make sure we have a closed system there. So the ties are really, they keep the concrete from bursting or like popping off the edges of our rebar. Our rebar is trying to buckle. They're very small, slender elements. The thing that's stopping them from buckling is the concrete. So the ties kind of help keep all of that buckling load for the steel internally. We also saw when our concrete cylinders failed, they all failed by busting out the sides, or almost a weird little tension phenomenon on the perimeter. The ties help make sure our concrete doesn't burst prior to us reaching the full capacity of our concrete and steel. Why is this neat? Well, the column is composite. We know that the strain must be the same for the steel and the concrete. We saw that last week. If they're sharing load, they have to be moving together. If they're moving together, they have the same delta of length, which means they must have the same strain. Because it doesn't matter what material it is, if they're moving the same amount and have the same original length, cross-section area is irrelevant in this, they must have the same strain. Well, steel is much stiffer than concrete. We know that the E is 200,000 MPa, and the E of concrete varies, but let's say somewhere around 30,000 MPa or less. So the steel stress will be much higher than the concrete stress because they have the same strain. And remember, there's that relationship between stress and strain. The steel will start to yield before the concrete reaches its full capacity, but it's still carrying its load. It'll start to deform more, but we can then have equal strain across the system. So the steel will continue to yield, we like yielding, until the concrete finally reaches its full strain. So the steel will keep having its strain increase because it'll deflect or deform at a faster rate. And we use the best parts of both of these materials all the way to the limit. So we like steel yielding, we like concrete to reach its full strength. These two things in combination in this system actually lets us get it. It's the fact that steel has this massive yielding capacity to it that makes this kind of such a brilliant system. And this wasn't something people calculated and figured out. It's a thing we've calculated and figured out after we've been using it for a really long time. We just knew that this was a really good way to do this long before we had the numbers to put to it. Okay, let's take a look at what this concrete column formula actually looks like. Well, let's do our PR naught or O, let's call it naught. PR naught is the compressive resistance of the concrete plus the compressive resistance of the steel. This is very similar. This is exactly what we were writing out last week for a concrete column. So the PR naught is the column resistance with no eccentricity. Eccentricity is what would apply some moment into our system. PRC is the resistance of the concrete, PRS the resistance due to steel, or the capacity of the steel or the concrete. So the equation for the concrete is alpha times our reduction factor times F prime C times the area of concrete. Well, this alpha is 0.8. You're just going to use 0.8. It has a relationship to the strength of the steel, and it has to do with uneven distribution within the concrete of aggregates. You don't need to worry about that. I'm going to tell you to use 0.8, or I'll tell you something very specific to use as alpha. The reduction factor for concrete is 0.65, so we already know this number. F prime C is the specified concrete strength, which we're picking. We're telling people what concrete strength we need to use. And that might be somewhere between 25 to 35 MPa. And then AC is just the area of the concrete. So there's nothing in this that looks different. The only thing different is this alpha, which I've told you is just a factor that we deal with concrete about distribution of material within it. Well, this is the same equation for compression of steel that we've always looked at. Our reduction factor times our stress times our area of our steel. And then our total capacity of our column is 0.8 this PR naught. Or we say nothing ever gets built perfectly. There might be some eccentricity within this column or the load within this column. So we'll just say, fuck it, only take 80% of whatever we calculate. And that's going to be the limit of how strong we say this thing is. So we reduce our concrete, we reduce our capacity of our steel, and then when we're done that, we reduce the capacity of the whole thing because we don't really know how perfect it's going to be when it's built. Remember, steel we have a lot of control over. Concrete, if you've ever seen how they get concrete to the upper floors of a high-rise building, they take it from a truck, they dump it in a bucket, they lift the bucket up, and they open up the bucket and it dumps in. So we don't have as much control over how perfectly everything is built. So remember that transform section phenomena we talked about last week? This is where it starts to be really handy for us. We could write the steel as the area as a ratio of the concrete and steel area, which we looked at doing last week. And then we can take a shortcut. We always love shortcuts. Engineers will do everything they can to find a shortcut unless we get stubborn, and then we make it as hard as we possibly can. But this is one of the places where we got tired of doing the long, hard, complicated systems all the time, so we made a shortcut. Rho. Rho is the area of the steel divided by the gross area, or the area of the concrete and the steel. Our new compression equation, if we use this rho as the area of the steel compared to the gross area, gross being total area, our PR naught is our gross area, which is, remember we had area in each of those equations. Well, for the steel, instead of using the steel area, we'll use our transformed ratio times our reduction factor times our stress. And then whatever's left had to be concrete. So 1, which is the entirety of the concrete, minus rho, or its percentage, times our alpha, times our reduction factor for concrete, times our F prime C. And then we still multiply it by 80%. So all we've done is in kind of these two equations, we've taken the AC and the AS out and made it AG and replaced it with the percentage of the area that's concrete and the percentage of the area that's steel, having transformed steel to concrete. But there's another thing we have to consider here. That would be a nice, easy equation and we'd be done with it. But there's a weird thing about concrete. Steel, when we were designing all our columns, we knew that they were essentially pinned top and bottom. Or if you wanted to say a pin at the bottom and a roller at the top. So our steel column could compress, but it was braced by the floor at the upper level. Well, and that was just how we detailed things, and it worked out really well. Concrete, for good or for ill, isn't detailed that way. So our steel columns essentially had pins at the top and bottom. Concrete, because they're giant, or relatively speaking compared to steel, and because we cast them together with rebar connecting them, they are essentially a moment connection. And remember, what we've said is if there is moment, we have to design for the moment. So if we have a detail that includes a moment connection, we have to make sure we actually design it for that inherent moment. I'm worried my kids are waking up. So we have to design for that moment connection that we've got there. How do we do that? It's long and it's a pain in the butt. And it's way beyond the scope of this class because we've got axial loads and we've got moment due to it being moment connected top and bottom. And it's kind of going to seem that I'm going to say, oh, there's all this stuff we can do, but here's a really easy way to deal with it. And that is exactly 100% what I'm going to do. So we have tables where we can find the appropriate reinforcement ratio. So if we know what the moment is by having done the design that we would have done last term on the system, so we know what MF is and what CF is on this, we can figure out what the appropriate steel to concrete ratio we need to make both of those things work. This is what the beautiful table looks like. It's a clusterfuck of information. Even still, every time I go up and open this book, I have to take a look at it and kind of get my head around it. There's a lot happening on one very small graph. First, let's talk about this little diagram here. In the concrete book, handbook, there are pages and pages of this. It varies depending on what that concrete column is going to look like. So this particular graph is for concrete that is 30 MPa. We have FY of 400 MPa. That's going to be pretty standard. And then there is our H dimension and our B dimension. So instead of talking about D here, we're going to talk about H. So basically the two sides of our column. We're going to say equal reinforcement on all four sides. So if there's 5 bars on this side, there's 5 bars on this side, there's 5 bars on this side, and 5 bars on this side. And then the ratio between the dimension and where the steel is written right here. this number here is about dealing with our cover. So this area around the steel is our cover, and the cover varies depending on what application we're using. Remember, that's all about protecting our steel from fire. And this is a chart where the ratio between the dimension between bars is 70% of the ratio to the overall dimension of the column. I'm going to work through that calculation and show you what that looks like, but basically it's how far in is our steel in our concrete element, or how much of that overall dimension is left, because the stuff around the edges, we don't really use that much, or certainly not in bending. This side of the graph is our compressive resistance divided by our gross area. Remember, that gross area is including the amount of steel and the amount of concrete, but the steel has been transformed into concrete. And then our MR on this side divided by our gross area times H, just to make these things compatible. Don't worry too much about this. We're not going to spend any time talking about that. This is all about kind of stiffness, and I don't want to get into that. And then all of these lines are rows. Not as in lines of data, even though that technically is what this is, but this is a row of 0.03. So anywhere along this line, we can see what our PR and our MR ratio to our AG is. What the fuck am I saying with all this? The best way to explain it is to go through an example. So we'll do that. But these are the important bits of data that I want you to take away from these graphs. So let's take a look. What reinforcing do we need for a 350 by 350 column that has a PF of 2,000 kilonewtons and an MF of 150 kilonewton meters? The concrete strength is 30 MPa. The reinforcement should be equal on all sides, which is pretty common for a square column. And we need to determine the longitudinal reinforcement. If we assume that there's 30 millimeters of cover, that's a thing that we would normally look up. I'll tell you what the cover is because I don't want to add that into the mix, but it depends on if it's a beam, if it's a column, if it's a slab, if it's inside, if it's outside, if it's cast against earth. It's all about protecting that steel. So we have 30 millimeters of cover, which means from the edge of the concrete to the first bit of steel, there's 30 millimeters. But look, these are our ties, 10M ties around our bars. So that's what's keeping our column from bursting, and it's helping prevent cracking. And 25M longitudinal bars. So these are longitudinal bars. I have drawn 5 on each side here, but we don't know what it actually is. We need to design that. We've just been told that it's going to be equal on all sides. So it's up to us to figure out exactly how many bars we need on each side, or the total number of 25M bars we need to make this column work. So let's go through our normal procedure here to figure out this. So we have our concrete column here. You can see that I've written the 30 millimeters to the cover. I've written down here our, well, they're using it, our ratio of the dimension to the center and center of the bars relative to the outside face. Maybe it's center. We'll go through the calculation and I'll show you what this looks like. I always have to remind myself of this. Yeah. Okay, so let's take a look at this. So what do we know? We know F prime C equals 30 MPa. That's great. They've told us already what our F prime C is. We know our B is 350 millimeters. We know our H equals 350 millimeters. We know our cover is 30 millimeters. We know our ties are 10M or they have a diameter of approximately equal to 10 millimeters, and our bars are 25M, which have a diameter of pretty much equal to 25 millimeters. Now, one of the things we needed to figure out was the ratio or the dimension from the center of our bars. So we want to know what this dimension here is. We've got 30 millimeters of cover, 30 millimeters of cover. We've got two 10M bars, and we've got halfway to the center of two 25M bars to give us that dimension there. So we know we've got 350 minus 2 times 30 minus 10 times 2 minus half of a 25M bar, but on each side. So we can calculate that, and we get 245 millimeters. That means we can calculate what that ratio is. Really, what we're saying is we've got H on the top and H on the bottom, so we've got 245 divided by 350, we've got 70%. So that ratio of how far in the bars are relative to the overall dimension is 70%, where we're effectively taking 70% of the overall area to use within our calculations. And so this is all based on that in the graph. Now we can mostly forget about that, but we have a dimension there that we can use. So let's go a little bit further on this. So we know that we've got our ratio of 0.7. Let's talk about our areas here. We know that our gross area is 350 by 350, or we get 122,500 millimeters squared. So that's our gross area. That's our total dimension of this column. Well, let's see what kind of ratio we need of PR to AG. So we don't know what PR, we know what PR we need. We know that we have a PF of 2,000 kilonewtons. So we want something, we want a PR that's at least 2,000 kilonewtons. So this is what we've always done, where we compare our capacity to our applied loads. So if we know what PF is, we know we need a PR of at least that to work. So our PR was 2,000 kilonewtons, but we're talking about things in millimeters and MPa. So we've got to multiply it by 1,000 because it was in kilonewtons. And then we can divide it by our gross area. We calculate this out and we get 16.32. Let's do the same thing for our MR. And it's MR times H. So we know that we had an MR of 150 kilonewton meters. Now, kilonewton meters, we need to change that to Newton millimeters. So multiply it by 1,000 to change it to newtons. and multiply it by 1,000 to change it to millimeters. And then again, our gross area times h, which was 350. We calculate this and we get an MR over AGH of 3.5. So we have these two handy numbers. Let's take a look on one of these graph charts. So PR over AG, we come on it and we find 16.3. We come over here to our MR over AGH and we find 3.5. We're on our F prime C 30 MPa chart, which is right, that we were told 30 MPa. It's a ratio of 0.7, which we calculated we would have, and we have reinforcement equal on all sides. So we draw these two red lines, and we see which of these bar lines they fall on, or if they fall somewhere in between. But it looks like our lines cross right here, which is convenient that it's directly on one of these lines. And for us, it's a row of 0.04. If it had fallen right here, it would be a row of 0.03. If it was in between these two lines, it would be a row of 0.035. So we get to use a row of 0.05. So for us, our row is 0.04. So that's something now that we can take away from this. So what do we do with that information now? So we know that rho is AS divided by AG, or the gross area. We want to know what area of steel we need. So the area of steel is rho times AG, which means we have 0.04 times 122,500. We can calculate the area of steel we need is 4,900 millimeters squared. That's great. We now know what area of steel we need. Now this is where doing concrete can be a slight bit iterative. That ratio that we calculated was based on it being 25 M-bars. So obviously we're going to try to go with a 25 M-bar as our selection. But if they hadn't told us exactly what bar it was going to be, because what if we only needed like one 25 M-bar and it seemed a bit silly, maybe we could have used 2 or 3 15 M-bars instead, which might be the case in some scenarios. I want to show you all of the options, but we know we need 25. They ask specifically for 25 M-bars. But sometimes what we do is we go through this process, figure out how many bars we need, or how much area of steel we need. We've guessed at what diameter bar we're using. And then if we end up needing a different diameter bar, we're pretty darn close to the answer, but we'll go through the process again using the specific new diameter of bar where we change the ratio. So you can see it's a slight bit iterative doing it in this way, but people start to get pretty good at knowing what dimension bar to expect. So whether it's probably going to be a 25 M bar. So rarely when you've been doing this for a while do you need to redo the calculation. I'm going to set it up in a way that you don't need to redo these calculations because I think that would be evil. It's the process I want you to go through, not kind of destroying your minds trying to go through the same calculation 20 times. So let's just take a look at all of the kind of options here. So we could have a 10M, 15M, 20, 25, 30, 35, 45, and a 55 M. The area of these in millimeters squared, a 10M bar is about 100 millimeters, a 15M is about 200 millimeters, millimeters. Again, remember these are pretty much standard across the industry. 300, 500, 700, 1,000, 1,500, and 2,000. So how many bars would we need of each one of those? Well, we need 49 10M bars. 100 times 49 is our 4,900. That seems a bit crazy. 15 M's, we'd need 25 bars. 17 20M bars. 10 25M bars. 7, 5, 4, and 3. So we can see, as much as we've been told to use 25M bars, let's just face it, that seems crazy and that seems crazy. We don't like to use 45s and 55s unless we absolutely have to. 5 bars seems a little bit weird. We'd need at least 4 bars, one in each corner, but we need 1 more. We have to have equal reinforcing on all sides, which means we have to add 3 more bars that we don't need. So that one seems like a silly choice. Maybe 7, but still working with 30s is a bit of a pain. So the 17 20M bars or the 10 25M bars both seem like good options. I'm going to tell you that 17 bars is a lot to shove in a column that's only a 350 by 350. How would you know that? You wouldn't. That's experience telling me that. So again, that's why the question specifically said use 25M bars. So we need at least 10 25M bars. So let's draw that out. Here's our column. 1, 2, 3, 4. Let's draw this out. I'm not drawing it very well. Let's start putting them at the corners. Remember, we needed equal reinforcing on each side. So that gives us 4 of them. That gives us 8 bars, but we needed 10, 8, 9, 10. Well, that's not equal bars on all sides, so it looks like we need at least 12. Let's redraw these. So as much as we only need 10, we do need equal reinforcing on all sides. So look at this. We now have a 350 by 350 30 MPa column with 12 25M bars and 10M ties. You wouldn't know this, but probably, that should be an and. A 300 millimeters center to center. Not for you to worry about. I'm telling you, it's probably a pretty darn good thing to do. So, we now have a column that works. Here's all of the answer worked out for you guys on 2 pages. And here it is drawn out for you again, where I've kind of recapped all of the information in one illustration for you. So that's pretty much most of what we need to think about, except concrete is, we still have to worry about this buckling phenomena. Now, here's the great thing about concrete. It's not that strong. How is that good? Well, we often need a lot of it to make it work. And because we need a lot of it, we have some pretty big dimensions. So even though it's not a very stiff material, we need so much of it because it's not that strong that we end up with buckling not really being the governing factor of columns. Not always. It can happen, but it doesn't usually end up being the thing that governs. So, we have an equation that says when we can neglect slenderness. Again, I don't want you guys to worry about that. I'm going to give you problems where buckling or slenderness isn't going to govern our situation. Here's how we would go about this phenomenon though. Would you make me a coffee too? Dave?
Yeah.
You'd make me a coffee?
Yeah, are you paused?
No?
Okay, I'll get you a coffee.
Thank you. You can set it on the side so they don't have to see your fancy pajamas.
Okay.
So we have an equation for slenderness. K, remember that's that effective length where we say if we moment connect the tops and bottoms, we get a slightly different profile of how it would buckle. So we might get to shorten that effective length, which is good, especially when we're talking about buckling. And concrete tends to be moment connected top and bottom, so it tends to happen that way. M1 and M2 are the moments at the top and bottom. That's really just saying we need to think about if our moment isn't the worst at the middle. If the moment is worse at the top and bottom, we just have to change the way we think about the behavior of this. Again, this is beyond what we're talking about for you guys, but I want you to know we do talk about slenderness in concrete columns, but often we can do this check and the problem goes away. We can't use those same tables. If slenderness governs, we have to do a more intensive design process. And so it becomes a lot more work, but it's not something we can't do as engineers. You guys don't have the tools to do it right now. I don't have the time or the luxury to give you that info, but you can find it. You can research it, you can go to the concrete code. All of this stuff is straight from the concrete code. I'm more or less an interpreter for you for this information. Okay, let's talk about concrete beams and slabs in bending, because the slab is basically just a big, shallow beam, if you will. So a concrete beam in bending, we have to deal with the same thing. We have cover, so we need fire protection. This tends to be our governing bit of cover. We need cover on the sides too, but it doesn't tend to have an impact on how we design the system. This one is really important because as much as we call this H, we know D, which is steel and wood, is that really important dimension. We use H. You've probably all wondered why we've used D instead of H. Well, it's because we save D for the important bit that we're using. H is the overall dimension of it, but D, or the depth of that we get to use, is only down to the center of our steel bits that we have. We have to neglect the part that's for cover because the concrete will crack, it'll fail in tension, and our piece of rebar here is just not doing anything for us. These are the bits that are working at the bottom. So we need to know our cover. We have our bottom steel, which is what's doing the work for us. Top steel can do two things. Often it's just there to hold the rebar up for us, or the ties. I'll talk about the ties again in a second. If we have a column or a beam, mostly we have bending like this, but sometimes we can have reverse bending. I'm going to show you that in a few minutes. Reverse bending, we have compression on the bottom and tension on the top. Well, when we have tension on the top, we need steel on the top. So we call that AS prime, or just a way to indicate that it's steel at the top. The stirrups are our cracking or our shrinkage crack control. So they're also our ties or our stirrups, depends on what you want to call them. But we would have these at some regular spacing. And we're going to talk about that in a few minutes when we talk about shear elements. But they do mean that the distance to our working steel is governed by what that dimension is as well. Same way it was with the columns. H is the height, B is the width, D is the top to the center of working steel, or that dimension that kind of does the job for us. So what does the work for a concrete beam in bending? Well, the compressive zone, or the part that takes all of the top work, is the concrete at the top. So the concrete does all of the top work for compression. The tension zone, the steel does all the work. So remember, in a normal bending beam, compression at the top, tension on the bottom. Steel behaves great in tension, concrete behaves great in compression. So this is effectively what we're using. The rest of it does some jobs for other things, but when we're talking about bending, the part doing all the work is that bit of concrete up there and that bit of steel down here. Now, when we talked about basic bending, we drew stress profiles, and we looked at the top extreme fibers, so the top and bottom extreme fibers, and when they reach their ultimate stress. And that really drew that stress profile where we had neutral axes. It was zero stress at the middle because remember, strain remains zero right at the center line. So we had a straight plane, which means we had equal stress. Our strain was linear, our stress was linear, which meant we can kind of build our calculations from there. This looks a bit different, but some of the concepts are still the same. Again, you don't have to derive that. You didn't have to derive it last time. I took you through the exercise, but I'm going to show you really what kind of starts to shake out when we're dealing with concrete. There's an interesting phenomenon with concrete that we like to achieve. We can have balanced reinforcing, we can under-reinforce, and we can over-reinforce something. Remember when I was talking about the column, and we liked because our strain was the same, our steel started to yield, and then we got to use the full capacity of the concrete? Well, that's really what this is all about. Have we allowed concrete to do all its work? Under-reinforced means we didn't put enough steel in to let concrete get to its maximum stress. Over-reinforced means we put too much steel in and we don't let the concrete get to its maximum stress. And balanced means it's just right. It doesn't mean those are bad things. It just means we have to think about it. We like to under-reinforce our steel. So the steel yields before the concrete reaches F'(C). So that means our steel will continue to deform without any change in stress until the concrete has hit its maximum stress. So again, it's not a bad thing. It's often what we like to do. A lot of engineers will get really uptight and say, it has to be this way. We can have something over-reinforced. It just means our failure mechanism is slightly less easy to predict. And we have to make allowances because now it's going to start to behave in a brittle manner. Our concrete will fail, and our concrete fails in a brittle manner. In this situation, our steel and our concrete should fail at the exact same time. And that means we get ductile behavior, which is what we like. Super important when we're talking about seismic design. We really need things to be ductile for seismic design. So, under-reinforced is what we tend to strive for, and a lot of our tables tend to be built around it. So, I already talked about concrete and bending, that the concrete in the tension zone would crack, so we don't really get to use it. We're left with the steel. So, any concrete that's on the bottom side of our neutral axis, or the tension zone of our neutral axes, would be neglected. So any of the concrete down there, even though it's there, it's not doing anything for us. My coffee's arrived. So anything down there that's concrete, not doing anything for us. We might as well pretend it doesn't exist. We know that the beam will be under-reinforced, so the reinforcing steel and the concrete will both reach their design stresses. So our steel will reach that 400 Fy, and our concrete will reach our F'(C) of whatever the concrete is, somewhere between 20 and 35 MPa, and we're telling them what concrete mix to make. So we'll have some control over that. Don't worry about this too much, but the parabolic stress profile in the concrete can be approximated by a rectangular one. So you know how we get kind of funny stress profiles where it's at the top, it reaches the maximum bit and it comes down to something zero. I'm going to show you the stress profile in a second, but we essentially can approximate it as a rectangle, and then I'm going to show you this diagram that shows the stress distribution in concrete at various stages of loading. So, okay, so first thing first, here's our moment. We have compression at the top, tension at the bottom. The concrete at the bottom cracks because it's crap in tension, and we're left with the rebar doing all the work. So our neutral axis, you don't need to worry about this too much. There's ways to calculate the neutral axes, but it's an iterative process. We make a guess at what our rebar is, we design it, we check where our neutral axis is, we figure out where everything is, see if that's the right rebar to use. If it's wrong with the area and its location, we have to go back and do the system again. So usually designing this is 2 or 3 passes to get it right. Obviously we have cheats because we're lazy, but that's generally the way we do it. So all of this concrete, not doing any work for us. Neutral axes, so we're left with steel down here and concrete up here doing the work. So this is what our stress profile would start to look like. So this is all of the bit that's in compression. We'll call this C. The bit that's working for us is C. The distance from the top to the center of our steel, or our effective depth, is that right there. Our steel is taking all of the tension load. Our concrete is spreading all that load out in stress on it, where that's our maximum stress that we're going to see. Very explicitly, this is what the stress profile starts to look like. So stage 1, we start to load it up. Stage 2, it's getting more and more loaded. Stage 3, we've kind of reached our maximum stress, and you can see that it's pretty flat here and it's peaking over here. This is what they say is our rectangular stress block profile. Again, don't worry about it too much, but you can see this is our kind of strains, a representation of our strains there. So what does that look like when we take that approximated rectangular block of area of concrete? So here's our neutral axes. All of this concrete's crap and not doing anything. We're left with this concrete doing all the work for compression and this steel doing all the work for tension. This is what the strain distribution looks like, and this is what our stress block looks like. So our area of our steel is taking all the tension force as just a regular load. Our concrete is taking all of our compressive load up here, but it's spread over an area that goes into the page. And what does our stress block look like? We've got our alpha. Remember, that's just how the concrete is clumped together. That's our reduction factor for C, and that's F prime C. And then this, if this is C, the distance from the top down to the neutral axis is C, beta 1 is the ratio of the area that's actually doing the work, or according to our kind of statistical calculations of the area that's doing the work. How do you know what beta 1 is? Well, there are calculations for figuring out what beta 1 is, but let's take a look down here, because of course I'm going to show you cheats, obviously. So the part doing the tension work, the reduction factor for steel times the area of steel times Fy. CC, which is the concrete compressive load, is the alpha 1 times our reduction factor for C, or for concrete, times F prime C, times the area of concrete that's doing the work. So that's B into the page. Remember, this is kind of turned for us. So B, we've taken this and we've turned it like this, looking at it on its side. So our area of concrete is B, which is into the page for this one, times beta 1C. So this is really kind of the essence of our bending resistance calculation. You're sitting there thinking, what the fuck is she talking about? I can't do anything with that. I'm going to show you that it's actually pretty easy. So how do we know what beta C is? Well, we can actually figure it out because there's a relationship between what beta 1C has to be and what T is, and we can write it right here. You don't always actually have to know what beta 1 is to complete this calculation. Beta 1C is our tension divided by this portion of our concrete stress block profile, because it has to be, because those two things have to be failing at the same time because we've under reinforced it. And so MR is really just our tension load times D minus beta 1C divided by 2. I know, it seems a little too easy and a little too crazy that that's the simple calculation when steel and wood have these complex, crazy calculations. But I'm going to show you that for concrete, most of it is We have a few select kind of dimensions for concrete that we use, and most of them have been calculated 100 times, and we can pull them off of tables and use them as we need to, which is what we did for our columns. Slightly different for our beams, but not too far off. So always the best way to kind of explain it is with a calculation. So again, we guess kind of at what our makeup of our beam is going to look like. And again, we get pretty good at knowing what these look like. We guess at what it looks like, we check and see if it works. If it doesn't, we know whether we're way off or if we're pretty darn close. If we're pretty darn close, we manipulate the makeup of it just a little bit and do the calculation again. If we're way off base, we pick an extremely different beam makeup, like dimensions and D and cover, and go through the process again until we get one that works, that isn't kind of wasting money to solve the problem either. Remember, it was like the cheapest solution. So what is the moment capacity? I just want to make sure that this is still recording, that it didn't run out of space. Okay, we're still good. What is the moment capacity of a 400 by 600 concrete beam with 4 20M bars at the bottom, 10M ties at 300 center to center, and 40M cover if the F prime C is 30 MPa? All of this information is very much stuff you would see written on a set of drawings. This is very much a beam that you would see. These proportions look really good. This looks like something we would see out in the design community. But we want to know what MR is. Maybe somebody else is checking MF, what actually MF is. But we know we want to find what the MR of this is. So we can go through that process. Okay, so this is one where it's kind of really handy to have this open. We know that tension is the reduction factor for steel times the area of the steel times Fy. So we can actually kind of figure that out right now. Let's figure out what the area of steel is. Actually, I'm not going to break it up into two parts right now. The reduction factor for steel times the area of steel times the strength of steel. The reduction factor for steel rebar is 0.85. The area of steel, we have 4 times 300. Let's just go back. 20M bars have an area of 300 millimeters squared. We've been told we have 4 20M bars at the bottom. So we know we have 4 times 300, and then our Fy for steel is 400. We calculate this out, we get 408,000 newtons, or 408 kilonewtons. So the tension capacity in this beam is by the steel, and the steel is an easy part. We know that the top and the bottom have to fail together because it's an under-reinforced beam. How do you know it's an under-reinforced beam? I'm going to tell you it's an under-reinforced beam. That's pretty much the way we design things. So we know that if we have 4 20M bars at the bottom, we can only have a tensile resistance of 408 kilonewtons. That's an easy part. We can figure that out. We've known how to do the tensile capacity of steel since lecture 4 of this term. So how do we take that a little bit further? Well, we saw that beta 1 lowercase c was equal to T divided by alpha 1 reduction factor for concrete, F prime C times B. Well, beta 1C, I told you don't really need to worry about because we're going to work it out very easily for ourselves. We know that our TR is 408,000 newtons. Alpha 1 we know is 0.8. F prime C we know is 0.65. They told us that it is concrete that is 30 MPa. And we know that B, which is how wide this beam is 400. So beta 1C we can calculate 65.38 millimeters. So we're saying that this dimension right here is 65.38 millimeters. So if we know that, we can start to figure out what that stress block looks like. So let's go a little bit further. We know that MR is that tension force times D minus beta 1C divided by 2. Or really, what that distance is right there times the tension force. Or what is our moment couple? So MR equals tension times D minus beta 1C divided by 2. We know what our tension capacity is. We already calculated that. D, we haven't calculated D. D is from the top to the center of our rebar, which means all of this doesn't count in D. So our total depth was 600. Our total depth was 600. We know that there is the cover, which they told us was 40 millimeters. And then we have our 10M bar, which is 10. And then it's to the center of our working steel, which is 20 millimeters in diameter. So we want to the middle of it, so 20 divided by 2. So our working portion of this beam is only 540 millimeters deep. Oops. So we're saying that this dimension is 540 millimeters deep. We figured out that that bit is 65.38, and we want to know this dimension right here. So it's that total dimension minus half of that beta 1C. So D, which we figured out was 540, minus our beta 1C, which we figured out was 65.38 millimeters, divided by 2. So we calculate this out, and we get 207 times 10 to the 6 Newton millimeters. Once we start talking about kilonewtons, or once we start talking about forces, moments, and tension and compression, we like to convert back to kilonewtons and meters. So this turns out to be 207 kilonewton meters. So this 600 by 400 beam with 4 20M bars, 40 millimeters of cover, and 10M ties at 300 center to center has an MR of 207 kilonewton meters. If we knew what MF on this system was, we'd be able to tell you if it worked or not. So we're starting to be able to do these calculations now. So there it is, all worked out for you. What are some other things we should think about? Well, a slab is just a wide, flat beam. So B is bigger, D is smaller. But it's not a big deal. The process is essentially the same. In fact, the slab is so wide that we stop and think about it in 1 meter segments at a time because it's a little bit easier to talk about. It's essentially a 1 meter segment beside another 1 meter segment times another 1 meter segment. And if we have bars at 200 millimeters on center, you know you'd have 5 bars in every 1 meter segment. And so that's how we handle the slab version of this beam calculation. Concrete beams aren't always rectangular. Because we have the ability to figure out what I is and what S is, we can start to really manipulate these systems and make use of other things or other bits that are involved in it. We can have T-shaped beams where we actually use where we might actually say that all of this is our beam. So we might actually increase the amount of concrete we have at the top. It's a more complex version of that calculation, but we can do it. I'm not going to make you guys do it, but I want you to know that the process is essentially the same. The ratio of the stress blocks gets slightly different, but the concept is the same. We like to ensure that the beam is under-reinforced for the basic premise to hold true. Again, I already talked to you about that. I'm only going to give you problems where we have under-reinforced beams. We can increase the bending resistance by adding reinforcement in the compression zone if we want. So if we have steel in the top, so that was that A prime steel, if we have steel up there, we can use it in that compression zone. We just do it similar to the way we did the compression calculation. So it's not doing quite as much work for us, but it is there, and we can improve the capacity of the overall system because we have a little bit of steel in that compressive zone. So it makes the calculation more complex because we're taking that compressive part of the calculation where we have steel and concrete together and throwing it into our bending calculation. Shear. Let's talk about what's happening in a beam for shear now. Concrete, its entire cross-sectional area is working for us. Steel, the ties are doing the work for us. If you guys remember, shear, which is like a bunch of little infinite planes, it's a plane slipping along its line, and we have an infinitesimal amount of those stacked side by side, which is really the principle of calculus. But we have all of these planes lined up side by side, and if we get a little bit of a failure here, and then a little bit of a failure here, and a little bit of a failure here, we actually start to see this kind of funny shape happen, and we get these kind of diagonal cracks along the side of a beam, and that's really indicative of a shear failure in a concrete beam. And so the way we want our steel isn't at the bottom to stop shear from going through. We want it, what you would think, is parallel to the shear plane, because if it starts to fail, the crack will start to kind of propagate sideways and it'll hit that piece of steel. So our shear reinforcing is actually these ties or stirrups that you'd see along the face of the beam. So this is what it would start to look like. This is often what we do with our stirrups. So you can see the stirrups here. There's bottom reinforcing. It's a beam that's built into a slab, and there's top steel to hold the stirrups and bottom steel that's doing our tension work. And then these are our stirrups. We can reinforce it with welded wire fabrics and inclined struts. I've never done those things, but here is what it's doing. So as we fail in tension, we get cracks here that start to propagate up the side. As these cracks propagate, they hit our stirrups and the steel takes over doing the work until our steel is doing the work in shear. So we have a shear limit on the concrete, and then we have a steel limit. We have a concrete limit on the shear and then a steel limit on the shear. But we can use those two things together if we want. It kind of works out to be something similar to our trusses, where these elements in here are technically doing the shear work of our truss, and the top and bottom chords are doing the tension and compression work of our chords. Don't worry about it too much. We're going to keep it nice and simple, and I'm just going to show you the very simple way to calculate our shear reinforcing. VR is the shear capacity of the concrete and the shear capacity of the steel. That's as simple as it is. Shear capacity of the steel is our reduction factor for steel, the area of our steel, Fy of steel, and then D divided by S. We'll talk about that in just a minute. So we'll talk about that in a minute. The shear capacity of the concrete, again, a lot of this, we looked at steel and wood where we take 2/3 of it. Concrete has a few more kind of inherent flaws on it. We like to use F'(C). In wood, we went and looked at exactly what the shear stress was, and it was much lower than our bending and compression capacities. And then we still took 2/3 of it. But we only have one way to check what our stress is for concrete, and that's compressive stress. So we have to have a relationship between our shear stress and our compressive stress, and that's what this equation is. So here's our normal B times W, which is our area. We know that shear is normally a reduction factor times our strength times our area, and then usually some factor for the fact that it has a funny stress profile. All of this is the funny, well, this and the square root are the funny stress profile. B and D is our area. There's our reduction factor for concrete. 0.2 and the square root of F'(C) is just dealing with so that the square root is bringing our compressive strength down so we can treat it for shear. The 0.2 is kind of like our 2/3 in our wood and concrete. This lambda is about the strength of the concrete. So we're going to be dealing with normal concrete. I don't want you to worry about anything else. We're going to deal with normal concrete. B is the width, and D is our effective depth of our column, or our beam. So we don't get to use that bit on the bottom, we only get to use the effective depth. AV is the cross-sectional area of the reinforcing steel crossing the tension plane. What does that mean? It is what are the area of the legs of our stirrups, essentially. So the fact is, though, that a stirrup goes up both sides of the column. So if you have a 10M stirrup that it's crossing, you have 2 of those because there's a leg on each side. So the area is actually double what the actual area is. And then over some distance, we have so many bars that we might cross. So if we have 10M stirrups at 300, we would have 3.33 bars over a 1 meter length, for example. So AV equals the cross-sectional area of the bar times the number of vertical legs, and S is the spacing of the stirrups. So again, I always find the best way to learn is by example. Let's take a look at that exact same beam that we had before. It's a 600M, in fact, it's all the same information here, but now we just want to know what the shear capacity is. So we have 4 20M bars at the bottom, it's a 600 by 400 beam, we've got 40 millimeters cover, F'(C) is 30 MPa, all the same information. The stirrups are at 200 millimeters center to center, and it's 10M ties. So we want to know what the shear capacity of this beam is. So let's go through the calculation. We know, the shear capacity of the concrete is 0.2 lambda times the reduction factor for concrete times the square root of F'(C) times the effective width times D. Well, we already calculated D earlier, we found that it was 540. It's the same beam, same equation. So we know that D is 540. So 0.2. We know that lambda is 1 if it's normal density concrete, which of course is what we're doing. The reduction factor for concrete is 0.65. Square root of 30 MPa times 400, which was the width of our beam, times D, which is 540. We calculate this and we get 153,800 newtons. I'm just noticing in my notes it says millimeters squared. Obviously we're talking about a VR. It's got to be in kilonewtons, not millimeters squared. So this is the same thing as 153.8 kilonewtons. Let's look at the shear capacity of the steel, which is our reduction factor for steel times our shear area of steel times our Fy, or our strength of steel, times D divided by S. So D is, this is about a ratio of how much steel we see in this zone. So let's take a look at this. We know that our reduction factor for steel is 0.85. The area of steel, we have 10 M bars, which is only 100 millimeters squared for a 10 M bar, but we have 2 of them. So 2 times 100 is the area of our steel, times Fy, which is 400, times D, which is 540, divided by our spacing, which we had 200 millimeters, I believe. So every 200 millimeters, there's one of these strips. So the shear capacity of the steel is 183,600 newtons. Again, it's written millimeters squared in the notes that I have written in the thing, but we know it's newtons, which is 183.6 kilonewtons. Often, because we're lazy engineers, if we do the calculation and VC is enough of the capacity, if the shear capacity of the concrete alone works, we won't even bother going further with the calculation. If we only had a shear of 100 on this, I probably wouldn't keep going with this calculation. I'd just say, yeah, it works for shear. If I had 200 kilonewtons of shear, factored shear in this, I'd need to figure out that VR was my VC plus my VS, or 153.8 plus 183.6 equals 307.4 kilonewtons. So now we can figure out, we have the shear capacity of that beam. So here it is worked out. This is where I was a total kook and put millimeters squared, but we know that that's supposed to be kilonewtons. There's another interesting thing with beams. Remember, our columns are actually moment connected at the top. Well, our beams in concrete aren't pinned. So this would be a series of steel beams and the moment diagram on them if they had a line load on it. Concrete, because we kind of embed that rebar into the slab and we carry our rebar through things, this, because we're moment connected at our support points, we would actually have a moment diagram that looked like this. Again, it's beyond the scope of this class for you guys to calculate what that moment diagram is, but we actually tend to have moment at the ends of our beams, which is kind of handy because look at the MF for this profile. Same load, same dimensions on both of these systems. MF is 45 kilonewton meters for all of these beams. So we need to design this for 45 kilonewton meters of rebar on the bottom. The continuous beam, we have 30 at the top and 19 to 15 at the bottom. So we would have to design for that steel at the bottom and that steel at the top in reverse bending. Often we have some rebar up here anyway to hold the ties, and that we don't often use in our calculation. We, in these zones right here, can just add a bar or two. So often, so if this is a beam, and there's a support here, and a support here, our bottom steel will carry through, and we'll design top steel in those zones right there where we have reversed moment. So this is where our moment is bending in the other direction, and we have tension in these zones here. And remember, we already have a little bit of steel there anyway, often just to hold the strips. So we're adding some, but not a lot, and we're only doing it where we have that reverse bending. Again, this is a shakeout of the way we actually detail concrete. And so if we detail it that way, we might as well take advantage of it if we have to. So what are the takeaways? You should know the basic look of concrete slabs, beams, and columns. You should know that columns, the steel and concrete, takes compression, and that in beams, the concrete takes compression and shear, and the steel does the tension, maybe some compression, and shear. You should know how to calculate the reinforcement for a concrete column, calculate MR for an under-reinforced beam, calculate VR for a beam, and the general moment diagram of a continuous beam. You should also know what the stress profile looks like for a concrete beam. So with that tension arrow for the steel at the bottom and the stress block at the top. We know it looks nothing like our wood and steel ones, so it should be a somewhat obvious choice if, say, I don't know, there was a multiple choice where you had to assign what type of material it was for each different stress block. It's okay, Dave, I'm wrapping up. You can come in. Malcolm, do you want to come say hi? So that pretty much wraps it up. You guys have been absolutely lovely. You guys have been absolutely lovely. I'm sorry we had to wrap up our term in such a crazy way. Come here for a second. In some ways, it's been lovely that I've gotten to spend so much more time with my kids. It's a bit of an overwhelming thing that you're trying to do essentially 3 jobs at once now. And I feel like you guys had to suffer a big burden of that. The other thing is we're all in this together, and you guys have been wonderfully patient. I'll follow up with some more information about the exam, but be prepared. It will be in the normal exam time slot. So make sure you have access to a computer during that normal time slot. If any of you have kids or need to make special arrangements, we can communicate that. Obviously, we need to make sure it's a fair process. It's hard to do and has to be a multiple choice on Quercus. So I am trusting you guys to be good people here. We're in a world where we all have to trust each other right now. Obviously, you guys could cheat if you wanted to. I'm going to ask that if you cheat, at least pay attention to what the answers are from whoever you cheated with, so that you're taking something away from this course. I love you guys. I might follow up with a video as we get closer to the exam if I can, but it's been a real pleasure, and hopefully I get to see you guys all next year around school when we're all let out of our homes. I'll go say hi, everyone. No, you're going to be shy. Okay. Thanks, guys.